All right, Olivia, I think it's just you and me for Chemistry 2 at the moment. So I'm going to go through this. I'm sorry, this is my third time doing this, so hopefully it works out okay and you'll be able to get your notes at least. I'm hoping some of the videos have helped you out if you looked at some of the videos that have been embedded in here, that maybe those explain some things to you. But we'll go ahead and get started. I'm going to kind of go through it quickly. Pause it if you need to. If you have any questions, you can ask me, of course. But what happened is on day one, I had just a regular piece of paper out here, and I asked the kids, I told the kids the paper's made up of C6H10O5. Let me increase the size of this a little bit. All right, so I said, how many carbons, how many hydrogens, and how many oxygens is in paper then? In one molecule of paper, you have 6 carbons, you have 10 hydrogens, and you have 5 oxygens. So then I said, write down some observations. So of course, if you're looking at this paper here, some of your observations might be, there's a red line on it, it is lined with light blue stripes. There's 3 holes down the side. I mean, you could get a ruler out and measure it if you wanted to. Whatever you can come up with, they had some observations. So then I lit the paper on fire and I had them write down observations after burning, during and after burning. So during burning, they saw things like there was smoke, the paper did turn like this black color, there was flame, and they also noticed that not all of the paper burned. The flame went out before all of the paper burned, and I left it that way. So we noticed those things. Then we looked at an ice cube, and ice is composed of H2O. So I asked them how many hydrogens and how many oxygens. So there are 2 hydrogens and there are 1 oxygen in H2O. So when I first got the ice out, they observed that it's cold, it's solid, it's kind of clear. There's really not a whole lot to cube. There wasn't really a whole lot to observe with the ice other than that. And then I just left it out on the table for a little bit. And of course it began to melt. So you ask, okay, where are the observations now? Well, it's now liquid. There's still a little bit of solid left, but it's liquid. The liquid's not as cold. It's still clear. But those are some observations. So what we did with those 2 things, one of them was an example of a chemical reaction, and one of them was an example of a physical reaction. So I asked the kids what they thought which one was. So the physical reaction was the ice. Not the paper, was ice. And one of your classmates said that the reason behind this is because nothing changed with it. So nothing changed. And it changed into water to liquid, but they said it's still water. So nothing changed, still water. The chemical reaction was the paper, and I asked them why they thought that was the chemical reaction, and they said because there was less paper. Like something had happened. Something had happened, there was less paper, so something had changed. So then I know it says to look up definition, that's for you guys at home if you didn't get this. The actual definition, or what I want you guys to use as the definition for this, for a chemical reaction, is it produces 1 or more new substances. So for the paper example, C6H10O5, we burned the paper, and what you get when you burn paper, those gases that you see, that is some CO2 gas and some water vapor and some energy. Now you also have some of this left over because not all of the paper burns, so you have some of that left over too. But you can see where we went from this big molecule and it broke it down into gases, a solid to gases. Now the physical reaction, chemically the substance has not changed. Alright, substance hasn't changed. So when I had brought out the ice, it was H2O and it was a solid. As it melted, it was still H2O, it was just now liquid. And if I left it there long enough, it would evaporate into a gas, but it would still be H2O, it would be water vapor. Alright, so that's the difference between chemical and physical. So then we have some examples here, some learning checks. So we have a rusty nail, which is chemical because you get iron and in the presence of oxygen it becomes FeO. It's iron oxide, Fe2O3. So it's something new, it's chemical. Tarnishing silver is kind of similar to that. So it is chemical. Bleaching a stain is chemical. Tearing paper into it's still just paper no matter how many times you tear it, so it's physical. Burning a log is a lot like burning that paper, chemical. Sawing a log, physical. Fermenting grapes, making wine, that is chemical. You end up with new substances. Boiling water is physical, similar to the ice. Breaking glass, physical. Sour milk, chemical. Alright, so if you have any questions on those, let me know. This YouTube video is pretty good. It's got a couple. They show some Bill Nye videos. They walk through the 5 signs of chemical reactions, so make sure you get those down. Watch that video. It's not very long, so it shouldn't take too much time. Alright, now on day 2, I used to in the past, we would do s'mores pops. And we would make these s'mores pops. Now, explain what the recipe above is stating. What the recipe is stating is that you have to have 24 marshmallows, 1 chocolate bar, and 4 graham crackers in order to make 24 s'mores pops. Okay, if I have 12 marshmallows, I'm not going to make 24 normal sized s'mores pops. So I said, okay, once we have explained that, let's now use what we did here to explain what's happening here in this chemical reaction. So what is happening here is that I have 1 mole of carbon added to 1 mole of O2 to make CO2. Alright, and the same goes for this. If I only have a half a mole, like if I only had 12 marshmallows, if I only had half a mole of carbon, I'm not going to be able to make my CO2. Just like up here, I wasn't going to be able to make all my s'mores pops. Alright, so we'll talk a little bit more about that and the amounts of stuff. Alright, these symbols and what they mean. So we've got the plus symbol, and that's just going to separate your formulas. So like up above we had, what was it, carbon plus oxygen. So if I didn't have that plus sign, it looks like carbon monoxide, but it's not. I need a carbon plus oxygen. Alright, so that separates formulas. This arrow means produced. You'll hear me say produce. Sometimes you might hear me say yields. Up there I said made, but it's producing, it's yielding something. This triangle here, delta, it means that heat has been added to the reaction. S is solid, so it'll tell you if, like carbon up there was a solid, it's solid carbon. L is liquid, and G is gas, so like up above the O2 had a little G there, it meant that that was gas. And then AQ is aqueous, so it's in a water mixture, so it'll be kind of liquidy, but it'll be in water. That's what all those symbols mean. You'll see them here throughout the rest of chemistry. Alright, so then the last part of day 2, I asked them this. I said, use the following equation to answer these questions. So before I even start, I want to make sure you know this is my reactant side, this is my product side. These react to produce my product. So how many moles of aluminum are on the reactant side? Well, I'm looking here at the beginning of this thing. Well, here or the subscripts. On my reactant side, there is 1 mole of aluminum. On my product side, there are 2. And I asked your classmates, is this possible? Does it make sense? Why or why not? And it doesn't. Just like the s'mores pops, if I have a half bar of bark, I'm not going to be able to make 24 s'mores pops. If I only have 1 aluminum, I cannot make 2 aluminums. I cannot get an aluminum out of thin air. So 1 aluminum cannot make 2 aluminums. Alright, so that's the big thing. So this led us into day 3, which I am so sorry that you're getting this all at one big chunk. You can always stop it and watch the rest at some other time. This led us into day 3 in how to balance equations, because this is an equation. Like this can happen, just like s'mores pops can happen. You just need the right number of materials. I can't make a s'mores pop without the graham crackers. So I need to add some stuff here. Right? So day 3 is all about, okay, how do we change? We can only change the numbers in the front, and they're called coefficients. So how can I change these things so that the whole equation is balanced? Well, if I look here, I've got 2 aluminums, and what I've done with people that are first learning this, or people that are struggling with it, is I'll have them write down both elements, or however many elements there are in the equation. This one just happens to have 2. And I've got 1 aluminum here, and I've got 1 sulfur here on the reactant side. On my product side, I have 2 aluminums, and I have 3 sulfurs. So to get this to balance out, I'm going to put a 2 here in front of the aluminum, changes that to 2. I'm going to put a 3 here in front of the sulfur, it changes that to 3. Now it's all balanced. So I just needed a 2 and a 3. You can leave that blank. I tend to leave mine blank because that space is only there because I put it there. But it's a 1. If you leave it blank, we just assume that it's a 1. Now this video is, I think this is the one that's a little bit lengthy. You can watch it if you're struggling. It visually shows you what's happening and how we can add things. But it is a little lengthy, so you can either use it, don't use it, maybe kind of speed through it. That's what we did in class. We kind of went to a part, and then we sped it up a little bit, went to another piece of it. All right, now this just wants to know if they're balanced or not. So once again, if this helps you, you can do this line, and you can do sodium and nitrogen, sodium and nitrogen. I won't do that throughout the whole video, just so I can speed this up, but you can stop and do that. There's 1 sodium, there's 2 nitrogens, 1 sodium, 3 nitrogens. So it is not balanced. This one's not balanced. Now if you wanted to balance this thing, let's see here. I need to put a 3 here, that would give me 6. I would put a 2 here, that gives me 6. But it changed my sodiums to 2. So I would need to put a 2 there, right? Then everything is balanced. So it becomes, obviously I do this pretty quickly because I've been doing this for a while, and you guys will get to that point where you can do this pretty quickly. It's all kind of like a puzzle. This one we just want to know if it's balanced. There's 2 carbons. Hydrogen, there's 4 here, but there's 2 right there, so it's 6 altogether. 1 oxygen. 2 carbons, 5 hydrogens plus that one, so there are 6, and 1 oxygen. So that one is already balanced for you. Alright? Okay. So here's balancing, and then the learning check, I'll just put the answers up here. You can pause the video, do it, and then check it, or however you want to do that. So here is some others. I'm not going to do that line down the middle from the reactants to the products. So what I'm going to look at first is, I know my irons are not balanced, but I'm going to wait because iron is by itself. So if I put a number here, it does not mess up anybody else. So I'm going to try to mess some things up first before that. So oxygen is 4. Oxygen is 1. I'm going to put a 4 here. So see how that now messes up my hydrogens? So we've got 8 hydrogens. So I'm going to put a 4 here. Now I have 8 hydrogens. So right now my oxygens are good and my hydrogens. Iron is 3. So I'm going to put a 3 here. So it is 1, 4, 3, 4, and everything is balanced. Alright, so right now if you want to pause this and try the learning checks, go ahead and pause now because I'm getting ready to just throw the answers up here. And if you have any questions, let me know, alright? So I'm going to go ahead and just put answers in these blanks, and then I'm going to erase them and move on. So learning check, the first learning check is 3, 1, 1. This one is 2, 3, 2. Alright, I'm going to go ahead and get those off of there. Alright, here's a short little video talking about polyatomic ions. You guys had a special sheet that had like PO4, SO4, NO3, all of these OH, all of those things on there last year. And so now that's what we're looking at. Last year we treated them like their own little element, and we're going to do it again this time. So we're going to look at Mg, Cl, Na, and we're going to look at PO4 as a single unit. We're not going to look at just phosphorus and oxygen, although you could do that, but it is much easier if you look at this thing as a single unit. Alright, so if I'm looking at this, right away I can see that my magnesium, I'm just going to pick one and I'm going to start with 8. You could have started with chlorine if you wanted, but I'm just going to go with magnesium, is 1, and it's 3 on the product side. So I'm going to put a 3 here. So right now magnesium is good. Let's look at chlorine now though. Chlorine is now 6. You're going to take that 3 times 2. Because remember, what this 3 means, it means that I have this molecule 3 times. So 2, 4, 6. That gives me 6 chlorines. So I'm going to put a 6 here. So now my magnesiums and my chlorines are good. So I'm going to look at my sodiums. That's 6. I need to put a 2 here. That's 6 sodiums. I've got 2 phosphates now, 2 PO4s, and I have 2 phosphates, 2 PO4s. So everything is balanced. 3, 2, 6, 1. All right, and then everything's good. Now I've got another